Okay. Now let's go to our topic, which is the cone beam computed tomography. Cone beam or the CBCT from now on, because it's a long name. Cone beam CBCT, it utilizes a cone-shaped X-ray beam and an X-ray detector. Now let's get back to we said that in the CAT scanner, that is the computerized axial tomography, what's happening is that the patient is being scanned by a fan-shaped X-ray beam. Okay, just like a fan this way. Okay, it's going to scan the patient, but in the CBCT, the X-ray shape is different. It is like a cone. Okay, so it's going to scan the patient it rotates around the patient in a cone. So then instead of being a thin X-ray, thin shaped X-ray, it will be in the form of a cone. So it will, instead of, just let's imagine it this way. I'm using my hand as a fan shape. Okay, I'm going to scan the patient in a fan, small area. Okay, but if I use like a cone, then I'm going to scan a larger area at the same time. So first of all, the shape of the X-ray is different. The scanned tissue is the scanned area, is bigger, so the scanning time is less. Okay, so it will utilize a cone-shaped X-ray beam and an X-ray detector. As you can see in here, the X-ray, when it is generated, it will go like in a cone. See the amount of the size of the beam, and it's going to rotate. Here the patient does not move. What the X-ray and the detector will move, and there is an image receptor that will capture all the X-rays after passing through the patient. Okay. The X-ray source, which is here, and the detector over here, they are going to rotate between 180 to 360. Actually, 360 cannot be achieved. The maximum that we can get is around 270. It's not a complete circle, so it's a start and then it ends at the other end. By so doing, it will scan the whole craniofacial structure. The three-dimensional data of the patient is acquired in a single rotation of the X-ray source and the detector. So it's one time rotates, we're done. Okay. So if we compare here the image in the fan scanner, there's a small size of a beam being collimated like a fan, and it's going to cover either the single slice or the multi-detectors. Okay, but in the CBCT, see the amount of coverage. Here it's like a cone, part of a drum, and here it is more of a rectangle. So the scanned area is bigger. So the first difference is the amount of the shape of the X-ray. As you can see here, in the CAT scanners, the patient moves, and it moves in a helical pattern, okay, in a spiral X-ray, and it scans. See the amount of scanned area, compare it to the amount of scanned area in the CBCT. So at the end, we will get 3D slice, like in a sagittal view, in a coronal view, and in an axial view. Okay. The majority of the CBCTs can scan the patient in a seated position. So either the patient sits, which is more preferable, of course, or the patient can scan while he is standing. But machines can be brought down to a sitting position, and they can do the scanning, especially in wheelchair patients. Scan times vary between 10 to 40 seconds. Scanning time depending on the scanner used and the exposure parameters which are selected. But this does not mean that the 10 to 24 seconds are all X-ray. Actually, the actual exposure time is only about 2 to 5 seconds in a pulsed scan. If you listen to a cone beam scanner while it's working, you will hear the pulsation, tick 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 tick. The whole rotation, it will take between 10 to 40, depends how much you want to scan and what area. But the actual time of X-ray production is between 2 to 5 seconds, and of course the exposure is less if it is compared to the CT or to the CAT scanners. The data which is acquired by the CBCT are captured in terms of volume, which are made up of voxels. I'll explain. Voxels are three-dimensional, and the voxels are isotropic. It means that they are equal in all three dimensions, which objects within the volume can be accurately measured in various directions. What is going on here? Unlike the CAT scanners, the computer is not stacking the two images 2D, 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 and then reformatting them. Here, the scan, because the voxels, the capturing units, differ in size, they are equal in size, so the 3D data is captured in the first scan. Okay? The images can be displayed in three orthogonal planes: the axial, of course, axial from the top, sagittal from the side, and coronal from the front of the patient. This is one of the machines that we are using. This is the default image, and the default image, this is the axial view, this is a coronal view, and this is a sagittal view. This patient has a big lesion. I think it was a dentigerous cyst. See, in the sagittal view, this is a slice of the patient. There is no superimposition here, and when you're going to measure this distances, it's exactly the same. However, unfortunately, there is no soft tissue component, so you cannot know what's inside the lesion. Unlike the CAT scanners, you can toggle between soft tissue window and the hard tissue window. Here you cannot. Okay, this is the lesion over here. Okay, a lesion extending from the coronoid, the sigmoid notch, down to the angle of the mandible. This is the lesion from the front, and this is the lesion from the top. So what you can see it in three-dimensional objects. This image has been achieved by a single rotation of the scanner and the receptor. Okay, and you can do 3D reformatting of the image. You can, of course, this is depending on the signal that has received by the detector. You can go to a bone level or a soft tissue level, but the soft tissue level here is not specific. It's just a soft tissue that helps you, tells you that this is not bone. This is an axial view. This is the sagittal view of the lesion, and you can see here the coronal view of the same. Okay. This is a sagittal view here. See, this is the widest dimension of the lesion in the sagittal view. Now you can go navigate through the lesion in an axial in the sagittal view. So you can go from the most lateral to the most medial. Every move you're taking here is actually taking 0.3 of a millimeter. So you can know exactly the boundaries and the extension of the lesion from its very start to its very end. You can navigate slice by slice. The good thing here is that if you take the same patient in a CAT scanner, the slice thickness is more, so you cannot exactly locate, comparatively with the cone beam, where the end of or the start of the lesion, because it might fall within this 3 millimeter thick. But if you're going for a thinner slice, you can, even in those 3 millimeters, you can know where the extension of the lesion is. and here you can see the lesion. See the difference? This is in the most lateral, this is the most medial, and this is the widest thickness of the lesion. So you can know where exactly the lesion would be extended. This is a representation of what we meant by the voxel in the CBCT. Now on a computer screen, what you see in your computer is 2D pixel, not a voxel. When it is 3D, it was called a voxel. Okay. The CAT scanners, their voxels are not similar in their, or not identical in their sizes, so it is called anisotropic voxels. While in the and the CBCT scanners, the voxels are isotropic, so the images are captured directly in a 3D dimension. Okay. Sorry. Acquisition systems and the cone beam CT is the receptors. Those units which are going to receive the X-ray after passing through the patient, and these are most CBCT units for the maxillofacial applications use an image intensifier tube, which is called, abbreviated as ITT, charged coupled device. Sirona is being one example of this. So it is either image intensifier tube. This is actually an older system. The images need less X-ray, but in terms of resolution, it's less. The newer generations, it is composed of a flat panel imager, which was released lately. This requires a higher dose, but it gives you a better resolution of the image. The flat panel imager consists of cesium iodide scintillators applied to a thin film transistor made of amorphous silicon. So the base of the imaging unit is silicon, amorphous, on which spreaded is the cesium iodide scintillator. The older system uses a charged coupled device which captures the image. Regardless, both systems, they do capture X-rays. Both systems, the image intensifier tube and the flat panel imagers, can give you a 3D image. However, the systems or the resolution differs, and the amount of the X-ray needed also differ. Images produced with the image intensifying tube result in a more noise than the images from the flat panel imagers. And flat panel imagers need to be processed to reduce geometric distortions inherent in the detector configuration. For us dentists, these things, whether a voxel or a pixel, isotropic pixels and isotropic voxels, it doesn't mean much to us. At the end, we want an image that we want to use it for interpretation. These are two examples of X-ray. This is the Sirona, which uses, this is the X-ray source, by the way, and this is the image intensifier tube charged coupled device, this one. And this is the newer system, or a recent one, which is the made by flat panel imager. This is the X-ray tube over here, and this is the flat panel imager. The patient sits. Both systems, the patient is going to sit. The X-ray and the source, they are going to rotate, and the image is captured. Of course, there are so many manufacturers now in the market. So excuse me, you can choose what you like. We said that the image tube intensifiers, they have more image noise. What we mean by noise, by definition, is the amount of black spots that are seen in the image which are irrelevant to the tissues. So you see too many black dots that are distributed all over the image, but it does not actually present the image of a structure. It is because of the scattering effect of the X-ray within the tissues. See, compare between this here. Can you read this? Can you read this? Here you can also. Because of the image noise, increased image noise, the image resolution decreases, the image quality decreases, and hence sometimes you might suppose here you're looking for a very fine extension of a lesion. If there is too much image noise, this will reduce the interpretive activity or the ability of the radiograph for a better image. Okay. The field of view, which is abbreviated as FOV, field of view is established by collimating, reducing the size of the primary X-ray beam, okay, limiting the X-ray radiation to the region of interest, or what is abbreviated as ROI, to reduce the effective dose by exposing only the subset or the part of the tissue and the organs. See, suppose you're doing an endo treatment or you're doing an extraction for a lower 8. Why should you expose the whole craniofacial structure for looking for a tooth which is impacted? So if you have the ability to reduce the field of view to the size that you want, you are going to spare the patient or unnecessary exposure to radiation. Of course, machines with limit or that can provide different fields of views according to the need, of course it's more preferable. Okay, maximum field of view differs between cone beam CT machines. Small FOV beginning at 3 by 4 by 4, see here it's 3-dimensional like Aquitomo, 3D Aquitomo, and large FOV machines up to 20 by 20 by 20 centimeters like the Newton 3G. So what do you need the machine for? Are you you're doing orthodontic surgery, where you want to see the whole maxilla and the mandible, or you're doing only endo treatment and minor oral surgeries? Choose your machine according, or this, I would say, the field of view according to your needs. Many units offer multiple field of view, and this is the best, of course, suitable for mandibular, maxillary, and maxillofacial scans. So you can control the field of view. Restricting the field of view to the region of interest effectively reduces radiation dose, and this is a fact. The lesser the amount of tissue exposed, of course, the lesser is the radiation dose, and hence the effects. Of course, it improves image quality by reducing scattered radiation. Remember the image noise? We said that the thicker the tissue is exposed, the more is the image noise. So if you're going to reduce the field of view, you're going to reduce the scattering radiation, and then you will improve your image.